So, in this lecture we are going to show some examples of some commercial digital control solution. So, I will first talk about some example of digital power control integrated circuit IC, then I will show example of some digital control system solution like system level solution. Then what are the benefit of digital control, and I will also explain some benefit which are mentioned with those examples product data sheet, and then I will show what are the important aspect in this course. So, some important application of power management. If we talk about the power management, one of the very important application is the automotive, and if you take automotive like in the car, it need not to be always electric vehicle. That means every car, if you go inside the the automotive, that means the body electronics, infotainment system, ADAS, these are independent of whether it is an electric vehicle or hybrid vehicle or even the conventional car. So, now all cars are going for more electrification, that means you will have more increasing use of electronic devices. But in addition to that, now for EV is a further electrification in the powertrain also. So, if you go for this automotive application, that means the audio and infotainment system, you have an increasing use of power electronics, that means power management. For example, if you go for audio, mostly the car are going for class D audio amplifier, which is a switch mode power converter. Then the infotainment system, you need like a dashboard, you need like a apart from audio, display devices, other computational devices. So, there is a huge amount of electronics and you need power for every electronic devices. Then the powertrain, the powertrain, if you go for electric vehicle, the powertrain is going to be electrified because you will be using the electric motors and then battery driven electric car, and it can be hybrid or fully electric vehicle. Then we will also have a charger for EV, that means it can be onboard charger or off-board charger, and those actually have a high level of power electronics, and where digital control also play a significant role. Then now there is an increasing need for ADAS for safety and security purpose, the advanced driver assistance system, where there will be real time communication between the satellite and the car. So, as a result you need a high speed communication as well as high speed computation, because there will be a lot of signal processing. So, as a result the computational load also increases. So, the challenges in the power electronics. So, then body electronics, then all this car also have a display like in LED driving, that means now it is increasing use of LED driving, LED load lighting for the car as well as the regular conventional like office application, house application, LED TV, everywhere the lighting application LED is coming up. Another example is the data center, where data center now everything is like a cloud server. So, that means we are accessing most of the computational facility where the actual computational load are sitting in somewhere else in the distance. So, here in the data center, even the server, now talking about the Google server standard where 48 volt to direct POL. So, if we are talking about the low voltage high current application where the voltage level can be 1.8 volt or below, the current can be several hundreds of ampere, or it can be even more than 1000 ampere when you are talking about the cloud server. So, for such application there are increasing use of digital control for power management control IC, and we will take some case study, some example case study. Now, we also have a increasing use of consumer electronics, particularly the mobile phone. So, like smartphone now becomes like a mini computer, and if you go inside the smartphone, we are actually making a video conferencing, we are playing games and we are talking. So, everything we are doing through mobile phone. So, mobile phone has a high dynamical load, and you need to meet like a very high computational demand, as well as you also need to ensure the battery life can be extended for a longer duration. So, all this require significant challenges of power management, where the digital power management is coming, so that you can actually meet this stringent requirement in terms of performance and efficiency. The another requirement is the 5G communication. So, if you talk about 5G communication, the bandwidth of communication is extremely high, and when you communicate, then actually your device has to also be compatible with the communication speed. So, as a result, the signal processing requirement in the computer as well as in the base station of the 5G communication is extremely high, because we are talking about it is similar to a server application where the current can be hundreds of ampere or 1000 ampere with low voltage application. Let us say it can be 3.3 volt, 1.8 volt or below. So, for such application, the computation load, the current load, like a type of load, so your control requirement become significant, and along with the power converter topology. So, you need to the digital controls are coming up very aggressively, all these applications. So, I am taking one example like 40 to 12 volt. That means, as I told, the server application where the Google server standard, it talk about 48 volt to POL, that means the server load. So, one of the requirement is a 48 volt to 12 volt, and then 12 volt in the downstream side, it can be a multi-phase converter, it can be a series capacitor, buck converter, there are many architecture. So, I am showing one example of 48 volt to 12 volt using an isolated converter, where it is the Infineon digital controller IC which is used to actually control this isolated converter. And this IC actually control, this is a plug and play, that means digital brick, that means multiple isolated brick converter can be controlled by this IC. Then this IC, since we are talking about multiple bricks, that means 48 to 12 volt, if the power requirement is high, then one such brick will not be enough, because its power rating can be typically few hundreds of watt, and if you need more and more wattage, so you can put such bricks in parallel, that means their input and output will be common, but for such parallel bricks you need to ensure that the current share among the bricks are like equal. Unequal current share can actually lead to potential damage. So, this controller also offer the current sharing, and also when you are going for if the load power level changes dynamically, then you need to shut down some of the bricks also. Then for one of these brick in the control logic, it uses a flux balance mechanism, because any isolated converter you have to be very careful about the control, and you have to ensure that the flux of the magnetic, that means the transformer, should not go to the saturation limit. That means you have to ensure that the flux are properly balanced, and you also need to ensure the flux are properly utilized. So, this flux balancing digital control, they use using flux balance method, but it is a voltage mode control, and this IC also offer like a GUI, graphical user interface support, and this is one of the example. You can get detail from the digital part number of the IC, and this also offer very high power density, because all the controller, compensator, logic, everything is inside the IC. Another example I am showing, which is the Renaissance digital power solution for data center, where we are talking about for 5G communication, cloud server, where the current level can be hundreds of ampere or 1000 ampere with a low voltage application. Here in this isolated, you can have a cloud server, like it can be 48 volt to POL application, it can be two stage architecture, where one stage can be hybrid switch capacitor followed by multi-phase, or it can be a LLC converter followed by multi-phase. So, there are such various architecture exist. Now, for this particular IC, what is written in the data sheet, that it uses a charge mode control, because when you go to digital, it is not necessary that whatever analog control we have designed, let us say for small signal based design, digital will be some Z domain of the small signal. No. So, digital control offer you more flexibility to implement nonlinear control, and this IC use something like a charge mode control for very fast transient response. So, you can get charge based control to implement near time optimal recovery, near time optimal control algorithm, and this actually IC uses a control logic where the current loop is inherently stable, although maybe detail may not be available, but in general if you use a variable frequency digital current mode control, I will be demonstrating in this course, you need not require any RAM compensation, because it is inherently stable, and that we know also. Another IC I am showing the MPS, monolithic power system solution, where this is a digital controller IC which is a centralized controller, and this is for multi-phase application, where the number of phase can increase significantly. It can be 8 phase, it can be 4 phase, and each phase has half bridge switch cell with driver integrated along with a current sensor, because you can see the current monitor, current sensing are coming out of the IC. So, these particular phases are optimized in terms of their capacity, that means they can in fact handle 30 and more than that ampere continuous current, and the peak current can be even high, and you need to balance all these phases, because the phase current balancing is important, and that is done by this controller IC. Then you need to do phase shifting, so that the ripple of the output capacitor can be reduced, so that the capacitor size can be reduced. And the third, also you need to do dynamic phase shading when the load current decreases. So, you need to maybe discard one of the phases, and you may need to consider only one phase if it is under light load. So, all this algorithm, that means, and this IC also use a nonlinear algorithm, because it need to achieve ultra fast transient, particularly when you go for VR13, VR14 specification, which specifications are not publicly available, but they are very stringent application. The undershoot overshoot requirement is very low, actually very stringent, and also the transient recovery time may be few cycles. So, to meet such algorithm requirement, maybe linear control may not work. So, either you have to go for nonlinear control, or we can go for large signal based tuning on control, which can actually meet such requirement. Otherwise, the small signal based control will not be sufficient. Then this control, since we will also have a combination of large signal and small signal. So, under small signal, this IC can operate like a constant on time control, where there can be automatic loop compensation, because in order to balance this current, you need to adaptively vary the on time. Then in order to meet a transient requirement or maybe phase shading, so this automatic loop compensation are possible. And also you need to ensure that you can meet certain desired switching frequency. So, you need some automatic loop compensation. Then the flexible phase management is useful to achieve high efficiency for a wide range of load current and input voltage. And then, since it is a digital control, all these controller component algorithm, everything inside the digital IC. So, you can reduce the component count and you can improve the power density. Another example is the Texas Instruments digital controller. This is particularly UCD3138. This controller IC is used to control the isolated DC-DC converter. One IC can control multiple isolated converter at a time, and also the same IC can be used to control various other isolated converters. So, that means this offers much feature for high peak and high light load efficiency. It will have a soft on off control, soft start also, and it support various isolated converters that I have discussed, and this also include all protection circuit. Now, so far we have discussed about the integrated solution, where either it can be a digital integrated controller or it can be a totally digital power management IC. But now we are talking about another example is the digital controller IC for PFC-LLC, particularly for LED driving application, for display application, and this particular IC actually can control both PFC and LLC together. So, it is a combo solution. It has the integrated startup logic with low standby power, and it uses digital multi-mode control, and it is used for a combo solution of PFC and LLC. So, this multi-mode control enable to achieve high efficiency over a wide load current range, and in this course we will be going to demonstrate multi-mode control along with the hardware case study using FPGA implementation. And multi-mode PFC is optimized, it can optimize efficiency for a wide range of load current. Then because of digital control, everything is inside the IC, so it reduces component count, so smaller size, and the parameter can be configured by means of hardware, software and firmware integration. So, that means you can tune the parameter from outside. Now, we are going to digital control system solution. So, one of the example is the ST microelectronics, and this is for PFC, interleave PFC solution, where this is the part number, one can go to the reference design. So, this particular IC use a digital controller which is a STM32 microcontroller, and in this course we will be going to demonstrate how to implement digital control using STM32 microcontroller. So, this particular reference design use a fully digital control solution, where it use a mixed signal average current mode control. So, in this course again we are going to demonstrate what is the architecture of mixed signal current mode control. Then this IC use input voltage feed forward. In fact, input voltage feed forward is necessary because we need to achieve unity power factor. So, the shape of the reference current should follow the rectified input voltage. So, that is why input voltage feed forward is essential, and this IC also use a load feed forward, because if you want to achieve very fast transient response, then you can use the feed forward. And I mean, all details are not available for this it is not available in public domain, but I believe load current feed forward can be helpful. If you use a constant on off time control, this load feed forward can help to adapt the on off time, so that you can achieve maybe pseudo switching frequency. That means you can achieve close, that means you can achieve nearly fixed switching frequency, and also the loop stability, the inherent current loop stability can be retained. And this particular solution also offer hardware software firmware integration. So, and this design is demonstration is for 3 kilowatt interleaved PFC, and it also offer very high efficiency. The another solution, which is a GAN based bidirectional totem pole PFC using Texas Instruments C2000 series microcontroller. In fact, this reference design will be demonstrated particularly as an example case study, because we will be considering how to implement digital control using C2000 series microcontroller. So, one case study at the end will be this particular reference design of GAN based totem pole PFC. Here it is a interleaved bridgeless totem pole PFC, and it is a fully digital multi loop control solution, and again it has a hardware software firmware integration, and this design for 3.3 kilowatt bidirectional PFC. So, that means this is used for particularly vehicle to grid and grid to vehicle integration, and then it also offer high efficiency and low total harmonic distortion. So, the example I have shown, what are the benefit? The digital control, since it are using let us say a microcontroller base or any other digital control, and particularly I have shown some IC which can be used for different topology. That means the design can be made flexible, so that you can use for varying topologies. Then if we go for HDL based implementation, which we will be talking in this course, you can actually make the design portable for other process technology. And I have told you that IC can accommodate large signal and small signal based control for very fast transient response and high efficiency. So, the controller can be reconfigurable. Then you can communicate, because now it is coming with PM bus communication. So, that means if there are multiple power converter, particularly for let us say mobile phone or even electric vehicle application, even for charger application, you need to communicate with the external devices, because you are actually taking charging from outside, or if you are plugging to an AC grid, or you are actually your charger is connected to the battery. So, you need to know the actual battery SOC status. So, that means that require a real time communication, and that is very much possible when your converter itself is working using digital control, because this inherent provide the digital data communication. So, by this way you can make the design reliable, fault tolerant, and the power supply network can be smart. And because of the digital solution, you can have a hardware software firmware integration. So, you will get an optimized solution, and you can also interface third party solution, and you can achieve high efficiency by playing with multi-mode solution and lower component count, because everything, all the components are inside the digital control IC, and you can implement advanced control logic like a digital nonlinear control, large signal based control to achieve very fast transient response along with a small signal control. Then you can have a digital power management IC solution, or you can have a digital control IC, for example, in multi-phase which control multiple phases, and or you can have a system level solution which can be a microcontroller for controlling PFC or LLC. And digital control can help initial development time, very fast rapid prototyping by means of FPGA initially you can develop or microcontroller. So, it can reduce the technology development as well as the product development time. And this course particularly is useful to familiarize different digital voltage and current mode control architecture under resource constraint. Then we will discuss different modeling technique, analysis and design method, and we will also discuss step how to validate the model. Then we will also discuss demonstrate Verilog coding and fixed point implementation and FPGA prototyping. We will also discuss different digital control demonstration case study using FPGA devices as well as STM32 and C2000 series microcontroller. And we will also introduce MATLAB customized model, and also will show the step for design validation. And finally, this course will be helpful to develop skilled manpower and to enable the indigenous intellectual property development. So, in summary, we have discussed some example of digital power control integrated circuit, we have discussed some example of digital control system solution, we have shown the benefit of digital power solution, and we have also discussed what are the important aspects in this course and how this course is going to benefit particularly for industry practitioner as well as the startup entrepreneur as well as the researcher who are working on the power electronics. That is it for today. Thank you very much.